This problem, we want to calculate the mole fractions of the products leaving a reactor where we're oxidizing N-hexane in air, and 50% of the N-hexane is oxidized, and 90% of that oxidation is going to carbon dioxide and water. The other 10% goes to CO and water. So let's first look at just a drawing representing what we're doing. And so what I've done is pick a basis, and the basis is 1 minute. I certainly could carry through the calculations in terms of moles per time, but it's easier just to look at number of moles. So we have two reactions. Let me write down the reactions first and then talk about it. So these are two reactions, and I've written them as balanced reactions. Now we have 20 moles coming in of hexane and 50% react, so that's 10 moles reacting per minute, and 90% is complete combustion, so that's 9 moles. So we're going to look at this reaction 9 times, and 10% or 1 mole, so 1 time for this reaction. Now in order to calculate mole fractions, we're going to have to look at how much oxygen, how much nitrogen we have fed to the system. So the feed for oxygen, if we assume it's about 21% of air is oxygen, so 21% of 500 moles. So we're feeding 105 moles. So that means the nitrogen feed 500 minus 105, so 395 moles of nitrogen. And then we're also interested in what's leaving the system. So we need to calculate how much oxygen we're using up. So the oxygen consumption, first reaction is 9 times 19 over 2 moles of oxygen. The second reaction is 1 times 13 over 2, and that's 92 moles of O2 that react. Well, we feed 105, react 92, so that means 13 moles of O2 in the exit, the effluent stream. Well, now we have enough information to fill out a table of moles and can use that to calculate mole fractions. So let me pause and insert a table. So here's the table where for this 1 minute basis, we have 20 moles coming in, we react half, so that means 10 moles are leaving. We don't have any moles of CO2, CO, or water entering, and we calculate that we have 105 moles of oxygen coming in, and we calculated that 13 moles leave, and we have 395 moles of nitrogen, and nitrogen doesn't react, so 395 leave. So for CO2, the first reaction is 9 times, each reaction 6 CO2, so 54 moles of CO2. Second reaction, 6 moles CO, and then water's in both reactions, so 9 times 7 for the first reaction plus 7, so that's 70 moles of water. Well, now we have the moles. We can calculate mole fractions. If we add up the number of moles, we have 548. So mole fraction, of course, for C6 is just 10 divided by 548 and 0.0182. Well, I'm going to do the rest of these divisions and write down the numbers while I pause. So those numbers are on a wet basis, meaning I've included water in the calculation of mole fraction, 548. Now I want to calculate on a dry basis, so that means I'm going to subtract the moles of water in order to have my new basis, so 470 moles of dry gas to get the mole fractions. Now for dry gas, I take 10 for C6 divided by 478. Of course, now the number is larger because water is not included. And I'm going to pause and write down the other moles. So there are the mole fractions, and you'll note that we don't have a mole fraction for water because this is on a dry basis, as if we've taken all the water out of the gas, and then we want to know the mole fraction. So that's what the problem's asking. Calculate the mole fractions on those two bases. And then what's the mole ratio of water to dry gas? Well, that mole ratio, 70 moles of water, and we calculate 478 moles of dry gas. So this is water to dry gas molar ratio. And that's what the last thing we wanted to do in this problem is calculate that.